Hello and welcome to this presentation on lower bounds for rainy differential privacy in a black box setting. My name is Tim Kutta, and today I'm presenting to you joint work with my collaborators, Martin Dunsche and Önder Askin. This project has been supported by the CASA Cybersecurity Cluster located at Ruhr University Bochum in Germany. So I want to start out this presentation by saying that I assume that you've had in the past some limited exposure to differential privacy. However, I want to make sure that we're all on the same page here, and therefore I'm just going to recap real quickly what differential privacy is all about. So let me start off by talking about the main idea or the conceptual aim of differential privacy. In differential privacy, we worried about users' data. Right? We're assuming that we have a bunch of people who are making up a database, and we are worried that in the course of a statistical study, we might leak information about the individual users. So say you're taking their average and you're publishing their average. Could an adversary infer that you were in the database or that I was in the database? This might be a problem, right? This might be a medical database, and you would really not like to for everyone or your insurer to know that you have a certain kind of condition, right? So how are we going to ensure your privacy? Well, the idea of differential privacy is kind of simple. Slap a little bit of randomness on the outputs, use a randomized algorithm, and then this randomness will mask individual small contributions of users. Let me be a little more precise with this. Suppose we have a database of people. Let's call it X for the moment. At the end of the day, we'll publish an algorithmic output, call it A of X. Now, we are now thinking about what does it mean to have a small contribution of one person, of this orange person in the first database. Now, to measure how strongly privacy impingement for this person is, we're swapping its data for another person's data. Let's say the blue person's data. Right, this gives us a new database. It's called an adjacent database because only one point in the database is different, and we're calling this database X prime. And this gives us its own algorithmic output, A of X prime. Now, A of X and A of X prime, they're both random, right? But if their distributions are similar to one another, an adversary wouldn't be able to tell if you're working on the database X or if you're working on the database X prime, and accordingly, they wouldn't really be able to tell if the orange person's in the database or if the blue person's in the database. And so we've achieved our aim of privacy. Now, this is the intuitive definition of privacy, but there are a lot of different ways to actually formalize differential privacy. And I just want to point out a few of them. So for example, there's pure differential privacy and approximate differential privacy. They have been around at the very beginning of differential privacy. More recently, there has been rainy differential privacy that has been introduced and is gaining popularity by the minute. There are a lot of different further notions of privacy, and I just wanted to point out like randomized differential privacy, but there are a lot of them out there. I could probably fill an entire slide with different privacy notions. But for this talk, I'm going to focus on pure, approximate, and rainy differential privacy. Now, pure differential privacy is very popular and it's used a lot in practice. However, it is a notion that can be a little too hot. What am I saying here? So what I want to say is that it excludes a lot of important algorithms that are actually used in practice. One important example is the Gaussian mechanism. The Gaussian mechanism is used all over differential privacy application, but pure differential privacy does not include it. Right? And so it's a little bit of a too stringent notion. And there are other important privacy methods that are not included by it, including shuffling, resampling, and so on. And we're a little worried about these things. Now, then there is approximate differential privacy. Approximate differential privacy tries to cut algorithms a little bit of a slack here. Unfortunately, this turns out to be too much. Approximate differential privacy isn't too hot, it is too cold. Approximate differential privacy includes too many algorithms. It even includes some where they are patently not private by anyone's standards. So for example, it allows us to publish an entire database with everyone's information with a very low probability. And this is not what I had in mind when I was thinking about privacy. So if we have notions that are a little too hot and a little too cold, rating differential privacy tries to sit in the sweet spot in the middle. It tries to be just right. It includes a lot of differential privacy algorithms that are excluded by pure differential privacy, but it also avoids the pathologies, these pathological examples included in approximate differential privacy. So what we believe is that it's a notion that is in some sense just right. So in this talk, I'll talk about how to assess rating differential privacy. And how do you assess differential privacy of an algorithm in general, you might ask? Well, as a rule, this turns out to be a paper and pencil task, right? So you actually write down the pseudocode of your algorithm and you start cranking it out. Now, if you can prove that an algorithm is differentially private, you might still be a little worried about its privacy guarantees. As people say, I've proved that it's correct. Now I just have to find out if it actually is correct. However, there are also other problems that your algorithm might face in reality. Maybe you proved that it's correct. Maybe it's actually differentially private, but maybe the implementation of you is not correct, right? So there are a lot of stumbling blocks here. And so what people believe is that it would be nice to have, just as checkups, black box methods that take outputs of your algorithm and then just statistically assess whether your algorithm is differentially private or not, right? And for pure differential privacy, there have been a lot of those methods been developed. So for just to name two examples, there's a paper from Bichsel et al. From 2021. There's a paper from Askin et al. 2022. I've also been a co-author on this one. They try to statistically assess pure differential privacy in a black box setting. And at the end of the day, they give what is called a confidence interval, so a region of plausible values. And this can be used to debunk false privacy claims by algorithms. So they can be kind of a tool to see if your algorithm satisfies differential privacy or not, right? This is what you need confidence intervals for. Now, these notions are developed for pure differential privacy, and they cannot be used to assess a lot of algorithms that don't satisfy pure differential privacy, such as the Gaussian mechanism, subsampling, shuffling, noisy gradient descent, and a lot of other more techniques that are more adjacent to machine learning, right? But these would be covered by rainy differential privacy. So our idea now is to develop such tools in the case of rainy differential privacy, because it just seems a more reasonable notion of privacy. In order to explain to you what rainy differential privacy is all about, I'm now going to go a little formal, and I'll start by introducing the rainy divergence to you. So what is the rainy divergence? It's a measure of how close a pair of densities, call them P and Q, are to one another. So I've written down the rainy divergence here, and you don't have to understand the entirety of the formula, right? The idea is what counts. It is a sensible notion of comparing one density to another density. In our paper, we use different kinds of densities. They could, for example, be continuous or discrete, but to focus our attention in this talk, I'm going to talk about them as being continuous densities. As you can see, the rainy divergence also includes an additional parameter. It's called lambda. It has to be bigger than 1, and I'll talk about it a little more in just 1 second. So we have the definition of the rainy divergence here, and now it's time to actually define what we are interested in, that is rainy differential privacy. So we call an algorithm rainy differentially private with the parameters lambda and epsilon if for all adjacent databases x and x prime, the output distribution of a of x and a of x prime are close with respect to the rainy divergence. So if they're smaller than epsilon. Let me just unpack this a little more. X and x prime being adjacent means that they differ in one data point. We've seen this in the first slide of this talk where we exchanged the orange person for the blue person. These two databases were adjacent to each other. If epsilon is really, really small here, it means that the output distributions P and Q have to be really, really similar to one another, and your algorithm is very, very private. Lambda is a kind of stringency parameter. If lambda is really big, then Rayleigh differential privacy basically collapses to pure differential privacy. Do we want that? Absolutely not. We want to stay a little bit away from pure differential privacy. We want to get something more inclusive. So in practice, lambda is something more like 2 or 5 or 7. It gets a little more stringent with higher lambdas. Okay, so now we want to assess in a black box scenario if Rayleigh differential privacy is satisfied by an algorithm. So here we have the algorithm A, and we're looking at a bunch of replicated outputs, A of x1, A of x2, and so on. And we're looking at replicated outputs of A of x prime. So think about these as independent identically databases. Now we'll try to see if P and Q are close to one another. More precisely, what is our statistical task? We'll try to estimate the Rayleigh divergence for this pair of densities. This will be the key building block to see if A actually satisfies differential privacy. Moreover, we're not just going to estimate this object, we're going to give confidence intervals for it, because this is the key tool to debunk the wrong claims of faulty algorithms. So how are we going to do this? So we start by estimating this difference, this distance between P and Q. And it seems like this is a very straightforward task, right? There are good estimators for densities out there. And for example, the case of continuous densities, P and Q, I can use what are called kernel density estimators. They're good approximations for P and Q. And could it be so simple? Are we going to make it home for dinner early? Couldn't we just plug them in and look at the Rayleigh divergence of the estimators P hat and Q hat? Seems like the obvious first approach that you could take. So let's see how this works. So to understand the problems that occur with this approach, right, if you just apply it, I've chosen to slightly rewrite the Rayleigh divergence here. So what you can see here is the Rayleigh divergence of P hat and Q hat. And what you can see is that Q hat occurs somewhere in the denominator, right? And this is potentially bad, because if you have a value in the denominator and it is close to 0, as densities are for some values, then the estimate becomes really blown up. And you have something that fluctuates close to 0 in the denominator, then the entire estimator becomes really, really unstable. So it turns out that this is not quite the right approach. However, we're not the only ones who've wondered about differential privacy. And from pure differential privacy studies, we know what to do in this case, at least roughly. What you can do if you have such a ratio of densities, the simple thing is to just truncate this density or floor it or regularize it. What do I mean by this? So we'll take the maximum of Q hat with a small number tau that is, however, bounded away from 0. So Q hat cannot go too close to 0. The denominator cannot be too small, right? And we stabilize the entire estimator. And this is kind of a standard strategy to use here. And it turns out it's a pretty successful strategy too. So if tau is neither too big nor too small, you have to kind of choose it carefully. But then this estimator, the kind of floored estimator of differential privacy, it's actually going to be pretty close to the actual Rayleigh divergence. So are we done now? Was it like this one regularization step? Well, not so fast. We had 2 aims in mind. Do you remember? We wanted to estimate, but we also wanted to get a confidence interval. To get a confidence interval, you need to study the distribution of this object here. You have to understand its random fluctuations, or in the lingo of probability theory, you have to look at its convergence, right? So how does it behave for large samples? And it turns out that this is a really, really hard job. Why is it a hard job, right? So you have to study its convergence to get the confidence intervals, but it seems like it shouldn't be that hard. Why not? Because we know the distribution of P hat and Q hat. They are approximately normally distributed, right? Now the question is, like, if these two distributions if these two objects have a very nice distribution, why isn't this object here also following a nice kind distribution that we can understand? But there is a statistical reason to believe why it should. In statistics, you very often use what is called a delta method. The delta method means if you have something that is normally distributed, you transform it, the transformation is also normally distributed. So why isn't this working here? Well, the delta method only works if you have a differentiable transformation. So you get normal distribution plus differentiable transformation will give you something that is normally distributed. But this is not what we're seeing here, right? Why not? Well, we have this maximum that we introduced here. It solved one problem, but opened up another problem. It's not differentiable. It's pretty much looks like a ReLU function, right? Not quite, so tau is not zero, but it looks pretty much like a ReLU function. And this will mean that it's not differentiable, because we know from the study of neural networks, right, certainly that, ReLU functions are not differentiable. So that is a problem. But we might be able to fix it, right? And we'll be able to fix it in the same way that people fix it for neural networks. We just say, okay, we don't take the ReLU function, we take a soft max or a smooth max, right? To take kind of like the smooth version of the maximum of Q at and tau. So this part here is differentiable. So the entire thing is pretty much differentiable. And we call this new estimator D smooth. And it turns out that this does really the trick. So you take the smooth max here, and this object is approximately normally distributed. And I'm personally so happy about it, because this will end up giving us confidence intervals. And confidence intervals, they allow us to see if an algorithm is really, it gives us statistical lower bounds. It allows us to see if an algorithm is actually satisfying differential privacy claims or whether it isn't. Now, in our paper, this turns out to be quite an interesting task, right? So this is not straightforward. This is not just an intuition that we give in our paper. We actually give the mathematical and formal proofs to see that this method works. And so we have to be quite careful about how much you smooth and how you truncate, and we crank it out and develop the theory for this. But at the end of the day, this is just a formal proof that this intuitive approach should actually work. So how does this translate to reality? So I only have limited time here, so I'm just going to give you a glance of how our experiments look like in reality. So here you have a randomized algorithm. So for example, randomized response shuffled, and at 1 we see a red line, and this marks the true privacy claim of the algorithm, and it's actually true. So we set this to 1 by somehow standardizing it for different values of lambda. And we can talk about this in the poster session, how this actually works. But think about it. 1 is the actual privacy claim. And these blue things that you can see here are violin plots. They are violin plots created by making our statistical lower bounds in 1,000 simulation runs. So what you can see is that our lower bounds are actually doing a pretty good job, right? They're very close to the actual privacy claim. They're pretty tight, right? And they're usually really lower bounds, right? They're lower than the actual privacy claim. They're overshooting only in very rare cases, which is kind of the guarantee that a theory of confidence intervals is going to give you. Here's one more example of this. In the case of the Gaussian mechanism, you can see that sometimes they're overshooting. As a rule, they're very tight lower bounds, and the overshooting probability is small, and the user can make it as small as they want. Right? In our case, we wanted to have it smaller than 5%. You can see that these things here are consistently smaller than 5%. So this ends my presentation. Thanks a lot for listening to this. Thanks a lot for taking a look at lower bounds for Rayleigh differential privacy in a black box setting. I'd be thrilled if you came over to our poster session to talk a little bit more about how the experiments work, what we actually showed, which algorithms we took a look at, and how our theory works. Until then, I hope you enjoy the conference very much. Thanks a lot for zooming in. Have a great day.